Today we'll look at the electric fields of conductors, and recall that in a conductor you have the valence electrons detaching from the core of an atom and they move around quite freely, whereas with an insulator the electrons are not free to move around. So this conductor is initially in electrostatic equilibrium, and as you can imagine all the charges cancel, because if you had some excess charge you're going to get a shock if you touch that metal. So now suppose we add electrons to this conductor, and therefore these electrons are going to want to get away from each other as far as possible. So what happens is that the electrons spread out and they reside on the outer surface of the conductor, as shown here. So the mutual repulsion of all the charges on the surface of the conductor eventually creates that state of static equilibrium. And for uniform shapes like spheres and cylinders and planes, you're going to have a uniform charge density and an absence of an electric field inside the conductor. So if we suppose this here is our conductor and it has a thick surface, so it's a thick shell with a cavity inside, well, inside the body of that conductor and inside the cavity, the electric field is zero. So as you can imagine, the electric fields due to each of those charges are going to cancel each other out. And in non-uniform shapes, you'll also have an absence of an electric field inside a conductor. And this is best visualized if we apply an electric field outside the conductor. So in this case, we're going to choose a uniformly charged infinite plate that's much larger than the distance between the plate and the conductor. So if we choose a point in the middle of the conductor, well, this electric field is going to be uniform. So remember that it's going to be sigma on 2 epsilon naught, where this plate is sufficiently close to the conductor and sufficiently larger. So what we're going to have is an electric field vector that looks something like this. Now, in the presence of this positively charged plate, more electrons are going to be drawn towards that positive charge. So that's going to leave a positively charged region on the other side of the surface, and therefore this imbalance of charge is going to result in an electric field that's going to act in this direction. So at this particular point, you're going to have the positive charges have an electric field that points away from the positive charge, and the negative charges will have an electric field that's in the direction toward those negative charges. And if you sum up all the electric fields due to these charges, you're going to have a resultant that acts in this manner. So therefore you're going to have the electric field due to a superposition of all these charges cancelling the electric field due to this positively charged plate, and thereby an absence of an electric field inside the conductor. And as a consequence of electrostatic conditions, well, you're going to have the electric fields due to these charges in a tangent direction to the surface cancelling each other out. So as a consequence of electrostatic equilibrium on the surface of the conductor, you're going to have these electric field vectors from that external electric field being perpendicular to the surface. So for example, if we draw an electric field line from here, it's going to bend like this, such that the electric field vectors are going to be perpendicular to that surface, and another one that comes from here will look something like this. And on the other side, you're going to have it again being perpendicular and bend away from the conductor. Okay, so that's what the electric field is going to look like, with perpendicular components to the surface of the conductor, as a consequence of electrostatic equilibrium on the surface. So another electric field line is going to look something like this, and in the middle it'll look something like this. And I'll see you in the next video.